This video is about gravitational potential energy, which is another type of energy. Gravitational potential energy is the energy an object has as a result of its ability to fall. As long as it has a vertical displacement or height that it can move down, it can push or pull objects with its weight until it hits the bottom of that height. The variable for gravitational potential energy is EP, and the unit again is J for joule. All energy is measured in joules. So I'm going to show you why objects have this energy. Let's say that I have this orange box M attached to a rope that's attached to a pulley, which is attached to another object. Let's say that this object is on a frictionless surface. So if the surface that the other object is on is frictionless, that means that just because this orange box has the ability to fall and to be pulled down with gravity, this orange box can actually pull the other object a certain displacement with a certain amount of force. So just because it has the ability to fall and because it has a mass, it has energy. It has the ability to apply a force on that purple box for a displacement. Gravitational potential energy is the easiest type of energy to figure out the equation for. Because if this orange box is pulling down with the force equal to its mass times gravity, because that's the gravitational force on it, we can assume that the purple box is experiencing that same amount of force from the small box, just m times g, and the displacement that the purple box is moved over is exactly equal to the height that the orange box falls down. So if this orange box has a certain height that it can fall from, that means that it can displace another object by that exact amount of height and use its own force of gravity as the force on the other object. So because the work done is equal to the force times the displacement, here the work done by the orange box is going to be the force of gravity times the displacement. And I can see that the displacement that the purple box travels is exactly equal to the height of the orange box. So that means that the displacement is equal to the height, and I know that the equation for gravity is m times g. So that means that the total work that an object can do as a result of its height and mass is equal to m times g, the acceleration of gravity, times h. And that's the equation for the gravitational potential energy, m times g times h. So this is pretty simple to use. I'll give you a few examples. A 2-kilogram ball sits on top of a roof 4 meters above the ground. How much gravitational potential energy does it have? So pretty simple. We're given the mass. We're given g is always 9.81 on Earth, and the height is 4 meters. So the potential is m times g times h. So I multiply 2 kilograms times 9.81 meters per second squared times 4 meters. And that's equal to 78.5 joules. So this has exactly 78.5 joules of potential energy. Here's another example. It's a little more complicated. A 5-kilogram ball sits on top of a track that consists of a 10-meter long ramp at an angle of 30 degrees and a 5-meter long ramp at an angle of 60 degrees. How much gravitational potential energy does it have at the top of both ramps, and how much gravitational potential does it have at the top of the lower ramp? So I'm going to figure out how high up in the air it is, because gravitational potential only depends on the vertical height. It does not depend on any kind of diagonal height that you have on a ramp. That's a really common misconception. It only depends on the vertical height. Using trig, I can see that the vertical height of that first ramp is 8.7 meters, and the height of the second ramp is 2.5 meters, just 10 times sine of 60 and 5 times sine of 60. So when I add these together, I see that the total height that the ball has at the top is 11.2 meters, and the mass is 5, g is 9.81 meters per second squared. So multiplying these out, I can see that the potential energy here is 549 joules. So if it rolls down here, it's now only at that lower height of 8.7, so the height is 8.7, mass is 5, g is 9.81, so the potential energy is m times g times h, which is 427 joules. So that's how you calculate the potential energy at different heights. One thing you may have noticed is that the position you choose for your base height of 0 is completely arbitrary. When we get to conservation of energy, you will be able to choose any height to be 0 and still solve the problem. For example, you may be watching this video and looking over at something on a desk, and that thing may have a certain amount of potential energy because it has a certain amount of height relative to the floor. But that height isn't necessarily the farthest it can fall, because you may be on the second floor of a building. So it could potentially fall all the way to the ground outside if we consider that to be the total distance it can fall. And we can imagine a really crazy scenario where that ball just keeps rolling and rolling after it falls until it gets to the Grand Canyon, and when it's there, it could fall even more. So the exact height that an object can fall is kind of arbitrary. It's set by humans, As long as you keep the 0 point of that height consistent throughout your whole problem, the math will work out and make useful predictions. So don't worry too much if it seems arbitrary. It is ultimately. Like, what we decide to be 0 is based on what works for our problem. One last thing to note, often the phrase the work done by gravity is used as a code word for the object's starting gravitational potential energy. For example, if a 10 kilogram object falls 5 meters, the work done by gravity on the object equals the gravitational force times the displacement, which is equal to its potential energy, which there would be 490.5 joules. So that's what you have to know about gravitational potential energy.